Welcome back. Tonight, we're going to explore the calm physics of deep space, the rules that govern motion, balance, and stillness far beyond Earth. In deep space, motion does not require effort. When an object is moving through space, it continues moving unless something interferes. This principle is known as inertia, and it dominates nearly everything in the universe. There is no air in space, no friction, no resistance. Because of this, movement becomes smooth and predictable. A planet does not struggle to stay in orbit. A star does not strain to move through the galaxy. They follow paths shaped gently by gravity and time. Gravity in deep space does not pull sharply. It curves motion gradually. Over long periods, gravity creates stable orbits, paths that repeat again and again with very little variation. This is why planetary systems can exist for billions of years without collapsing. Change in deep space happens slowly. Even massive objects respond over enormous spans of time. Acceleration is subtle. Adjustment is minimal. Most of the universe exists in a state of near balance. Energy spreads evenly. Motion smooths out. Large systems resist sudden change. From a physics perspective, this stability is not accidental. It is the natural outcome of frictionless motion and gentle forces acting over time. When nothing interrupts a system, it settles. Stars orbit calmly around galactic centers. Galaxies drift in predictable patterns within clusters. Nothing needs constant correction. Nothing requires attention. The night sky appears still because, at these scales, motion unfolds slowly enough to feel permanent. Even light, moving at its maximum speed, can take thousands or millions of years to cross these distances. From our perspective, everything looks fixed. This appearance of stillness is not a lack of motion. It is motion stretched across time. Physics favors this kind of calm continuity. When forces are balanced and resistance is low, systems naturally remain stable. This is the dominant condition of the universe. In deep space, inertia is not a special case. It is the default condition. Inertia describes the tendency of an object to continue doing whatever it is already doing. If it is still, it remains still. If it is moving, it continues moving in the same direction and at the same speed, unless something interferes. On Earth, inertia is difficult to observe clearly. Air resistance, friction, and constant contact with surfaces interrupt motion almost immediately. Movement stops quickly. Energy is lost to heat, sound, and deformation. In space, those interruptions are largely absent. With no atmosphere and no surfaces to rub against, inertia dominates behavior. Objects do not slow down on their own. They do not need fuel to keep moving. They do not require correction. Once motion begins, it persists. This is why space travel relies so heavily on careful initial conditions. A small push, applied once, can result in motion that continues for years. A spacecraft coasts most of the time, not because engines are constantly firing, but because nothing is stopping it. This same principle applies to every natural object in the universe. Dust grains, drifting between stars, follow straight paths. Asteroids move through space without effort. Entire clouds of gas carry momentum accumulated over millions of years. Inertia is not dramatic. It is quiet, steady, and persistent. When gravity enters the picture, inertia does not disappear. Instead, the two combine. Gravity does not cancel motion. It bends it. When an object moving through space passes near a massive body, gravity curves its path rather than stopping it. The object continues moving forward, but its direction changes gradually. This balance between forward motion and gravitational curvature is what creates orbits. An orbit is not an object being held in place. It is an object continuously falling, while also continuously moving forward. From a physics perspective, a planet in orbit is always missing the surface it is falling toward. The planet keeps moving sideways, fast enough that the surface curves away beneath it. This idea applies at every scale. A moon orbits a planet orbits a star orbits the center of a galaxy orbits within a cluster. At no point does motion stop. At no point does gravity need to pull harder. The stability of these systems comes from balance, not force. Planetary systems form from rotating clouds of gas and dust. These clouds already possess motion before any planets exist. They inherit momentum from earlier events, nearby stellar activity, galactic rotation, and gravitational interactions. As the cloud collapses under gravity, it spins faster, not slower. This is a consequence of conservation of angular momentum. When matter moves inward, rotation increases. The same principle can be observed in everyday systems, scaled down dramatically. A spinning figure skater rotates faster when pulling their arms inward. The total momentum remains the same, but it is distributed differently. In space, this effect causes collapsing clouds to flatten into disks. These disks rotate smoothly. Within them, material follows predictable paths. Over time, small particles collide gently, stick together, and grow. Pebbles become rocks. Rocks become larger bodies. Eventually, planets emerge. None of this requires urgency. Planet formation is a slow process. It unfolds over millions of years. Each collision is minor. Each adjustment is gradual. Once planets form, they inherit the motion of the disk they came from. They do not need to find their orbits. They are already moving in the correct direction, at nearly the correct speed. Small gravitational interactions refine these paths over time. Orbits become smoother. Instabilities settle. What remains is a system that can persist for billions of years. From a distance, planetary systems appear orderly because inertia preserves motion and gravity maintains structure. There is no need for constant intervention. Even when disturbances occur, passing asteroids, minor collisions, or distant gravitational influences, the system absorbs them slowly. Large-scale change is rare. This is why our own solar system has remained stable for such a long time. The planets follow paths determined early in its history, adjusted only slightly over immense spans of time. The same principles apply to systems far larger than planets. Stars within galaxies follow orbital paths shaped by the combined mass of billions of other stars. Each star moves according to inertia, guided gently by gravity. No star chooses its path. No correction is required. The motion emerges naturally from the physics involved. At even larger scales, galaxies themselves move within clusters. Their paths are influenced by dark matter, shared gravitational fields, and ancient momentum carried forward from the early universe. Again, inertia dominates. The universe is not constantly restarting motion. It is continuing motion that began long ago. This continuity is one of the most calming aspects of physics at large scales. Nothing is frantic. Nothing is abrupt. When forces act, they act gently. When motion exists, it persists. Planetary systems are expressions of this principle made visible. They are long-lasting patterns of motion, maintained by balance rather than effort. Inertia ensures continuity. Gravity provides structure. Together, they create systems that endure. From the smallest grain of dust to entire planetary systems, the same rules apply. The scale changes, but the behavior does not. Motion continues. Paths curve smoothly. Stability emerges naturally. This is not a special condition. It is the normal state of the universe, and it has been this way for billions of years. Gravity is often described as a force, but at its most fundamental level, it is a relationship. It arises whenever there is mass. Any amount of mass, no matter how small, contributes to gravity. A single particle has gravity. The effect is extremely weak, but it exists. When two particles are near each other, each slightly influences the other. The interaction is subtle, continuous, and always present. Nothing switches gravity on or off. As more particles gather together, their combined gravitational influence increases, not suddenly, but cumulatively. A grain of dust contains trillions of particles. Together, their gravitational effect is still very small, but it is stronger than that of any single particle. As matter accumulates, gravity becomes easier to observe. This is how gravity operates everywhere in the universe, through addition rather than intensity. There is no threshold where gravity suddenly becomes important. It grows smoothly as mass increases. When gas and dust drift through space, gravity is always acting, even when motion appears random. Over long periods, slight imbalances matter. A region with slightly more mass than its surroundings will exert a slightly stronger gravitational pull. Nearby particles drift toward it, slowly. As they arrive, the mass increases. As the mass increases, the gravitational influence grows. This process is gradual and self-reinforcing. Clouds of gas do not collapse suddenly. They contract over immense spans of time. At the smallest scales, individual atoms drift. At larger scales, clumps begin to form. As gravity gathers material, motion becomes more organized. Particles that were once moving independently begin to respond to a shared center of mass. This is where gravity begins to shape structure. As material falls inward, it rarely moves straight toward the center. Small sideways motions add up. These sideways motions become rotation. Gravity does not eliminate motion. It redirects it. As matter collapses and rotates, paths curve instead of ending. Straight lines become arcs. This is the origin of orbital motion. An orbit does not require balance between two equal forces. It emerges naturally when inward attraction and forward motion coexist. At small scales, this can be difficult to visualize. At larger scales, it becomes clear. Consider a small object drifting past a larger one. Gravity pulls it inward, curving its path. If the object is moving slowly, it may collide or fall inward. If it is moving faster, it may swing past and continue on a curved trajectory. At just the right range of speeds, the path closes into a repeating curve. That curve is an orbit. This process does not require planning or adjustment. It arises automatically from the conditions involved. In planetary systems, gravity acts continuously and predictably. A planet does not stay in orbit by resisting gravity. It remains in orbit because its motion already matches the gravitational environment. The planet is always falling toward its star. It simply never reaches it. The surface curves away beneath the planet's path. This behavior is the same at every scale where gravity dominates. Electrons orbit atomic nuclei through different physical rules, but the conceptual pattern is similar. Motion constrained by attraction, resulting in stable paths. Moons orbit planets. Planets orbit stars. Stars orbit galactic centers. At each step, the underlying idea remains unchanged. Gravity shapes motion. Motion preserves continuity. When many objects interact gravitationally, their behavior becomes more complex, but not chaotic. Over time, unstable configurations resolve themselves. Paths adjust gradually. Objects that interact too strongly may collide or be ejected. Those that remain settle into long-lasting arrangements. This is why mature planetary systems appear orderly. Their early histories may involve interactions and rearrangements, but the outcome favors stability. Once established, orbits tend to persist. Small disturbances do not usually destroy them. They are absorbed and redistributed. Gravity works slowly, but it works constantly. It does not require awareness. It does not require correction. The structure of the solar system reflects this. The planets follow nearly circular orbits, not because circles are special, but because irregular paths tend to smooth out over time. Energy is exchanged. Angular momentum is redistributed. Eventually, the system reaches a configuration where changes are minimal. From a physics perspective, this is a low-energy state. Low-energy states are preferred. They are not forced into existence. They emerge naturally. This tendency toward stable arrangements is not unique to planetary systems. It appears wherever gravity operates over long periods. Star clusters settle into predictable shapes. Galaxies develop rotating disk and stable halos. Even clusters of galaxies follow large-scale patterns shaped by gravity and inertia combined. At each level, gravity organizes matter without urgency. There is no timetable. Processes that seem slow to us are simply unfolding at their natural pace. 1,000,000 years is a short interval in gravitational systems. 1 billion years is common. When observing the universe, what appears calm is often the result of motion spread across immense spans of time. Orbits feel permanent because the forces shaping them change very slowly. This slow evolution is a defining feature of gravity-dominated systems. Once matter is arranged into stable paths, it tends to remain that way, unless disturbed by something significant. Significant disturbances are rare. Most of the universe exists far from violent events. The average environment is quiet. Gravity continues to act everywhere, but it does so gently, from particles drifting through space to planets tracing long arcs around stars. The same principle applies. Mass attracts, motion continues, paths curve, structure emerges. This is not an exceptional condition. It is the default behavior of matter in a universe governed by gravity. And it is happening continuously, whether observed or not. Once gravity and motion establish an orbit, the next question is stability. An orbit is not just a path traced once. It is a path repeated over time. For an orbit to persist, small variations must not grow uncontrollably. They must remain bounded. This is where long-term gravitational order emerges. In space, objects rarely exist in isolation. Most orbits exist within systems, multiple bodies influencing one another simultaneously. Each object contributes a small gravitational effect to the others. Individually, these effects may be minor. Over time, they matter. In stable systems, these influences balance rather than compound. This balance is not static. It is dynamic. Planets experience tiny gravitational tugs from neighboring planets. Moons feel the influence of both their planet and the star they orbit. These forces do not cancel perfectly. They fluctuate. Yet, in many systems, these fluctuations repeat in predictable patterns. This predictability is what allows orbits to remain stable over millions or billions of years. One of the key mechanisms behind this stability is resonance. Orbital resonance occurs when two orbiting bodies have periods that form simple numerical ratios. For example, one object may orbit twice in the time it takes another to orbit once, or 3 times for every 2. These ratios cause gravitational interactions to repeat at regular intervals. When interactions repeat in a consistent way, their effects can reinforce order rather than disrupt it. Resonance does not always create instability. In many cases, it enhances stability. Repeated gravitational nudges can gently steer objects back toward predictable paths. This process acts like a form of correction, but without intention. The system does not try to stabilize itself. Stability emerges from repetition. Our own solar system contains multiple examples of this behavior. Moons around large planets often exist in resonant chains. Their orbital periods are linked. These relationships prevent close encounters and collisions. They space objects out naturally. Over time, unstable arrangements tend to disappear. Objects collide, merge, or are ejected. What remains is a configuration that resists change. This filtering process takes time. Early planetary systems may be chaotic. Over millions of years, that chaos diminishes. Paths that cross frequently do not last. Paths that remain separated persist. Eventually, the system reaches a state where changes are rare and gradual. From a physics standpoint, this is another example of systems moving toward lower energy states. Energy does not vanish. It redistributes. Highly energetic, irregular motion gives way to smoother, repeating motion. This transition is slow, but reliable. Orbital shapes also evolve. Highly elliptical orbits tend to become more circular over time through gravitational interactions. Circular orbits distribute energy evenly. They minimize extremes. Extreme configurations are less stable. As interactions continue, systems naturally drift toward configurations that require less adjustment. This process does not require symmetry or precision. It only requires time. Time allows small influences to accumulate. Time allows unstable paths to remove themselves from the system. In mature planetary systems, most remaining orbits are well separated and predictable. This predictability is not fragile. Small disturbances rarely destroy it. A passing object may slightly alter an orbit, but the system absorbs the change. Gravitational interactions spread the effect across the system. The result is resilience. At larger scales, the same principles apply. Stars orbit within galaxies under the combined gravitational influence of billions of other stars. Each star feels the pull of the entire galaxy, not just nearby neighbors. The resulting motion is smooth and collective. Stars do not collide often. They are spaced far apart. Their orbits persist for billions of years. Galaxies themselves move within clusters, following large-scale gravitational structures shaped by dark matter. These motions are slow and coherent. Even when galaxies interact, the process unfolds gradually. Disturbances propagate slowly through vast distances. This slowness is essential. It prevents sudden collapse or disruption. It allows systems to reorganize without breaking apart. From the smallest stable orbit to the largest gravitational structure, the same pattern appears. Motion repeats. Interactions average out. Order persists. Stability is not the absence of motion. It is motion that remains bounded. Bounded motion is predictable. Predictable motion requires little adjustment. This is why gravitational systems, once settled, feel calm. They are not static. They are simply not changing quickly. This slow pace defines the character of the universe at large scales. Rapid change exists, but it is localized. Supernovae, collisions, and energetic events occur, but they are rare relative to the vast quiet in between. Most matter spends most of its time in stable configurations. Gravity ensures continuity. Inertia preserves motion. Time smooths irregularities. Together, these factors produce long-lasting order. From particles gathering into clouds, to clouds forming stars, to stars anchoring planetary systems, the same rules apply. Stability is not imposed. It emerges. And once it emerges, it tends to endure. When we move beyond individual planetary systems, the same physical principles continue to apply, but across much larger distances. A planetary system occupies a relatively small region of space. Even the widest orbits around a star span distances that are tiny compared to the separation between stars. Between one star system and the next, there is a great deal of emptiness. This emptiness is not truly empty. It contains sparse gas, faint magnetic fields, and low levels of radiation. But it is quiet. Within this quiet, stars move. Each star carries the momentum it inherited when it formed. That motion persists for billions of years. Stars are not fixed points. They drift through space along paths shaped by gravity and inertia. These paths are not random. Stars form within large clouds of gas that already possess motion. When a cloud collapses and fragments, the stars that emerge share similar velocities. This creates groups of stars moving together through space. At first, these groups are tightly bound. They may form clusters containing hundreds or thousands of stars. Within a cluster, gravity links the stars loosely. Their mutual attraction is weak, but it is enough to keep them near one another for long periods. Over time, these clusters evolve. Stars interact gravitationally, exchanging small amounts of energy. Some stars gain slightly more speed and drift outward. Others slow and sink deeper into the cluster. Eventually, the cluster disperses. The stars do not scatter violently. They separate slowly. Each star continues along its own path, still following the overall motion it inherited. This gradual dispersal creates stellar neighborhoods. A stellar neighborhood is not a rigid structure. It is a region of space where stars share similar motions and histories. The stars within a neighborhood may be separated by many light years, yet still be moving in roughly the same direction. Their paths remain parallel over enormous distances. From a human perspective, these motions are imperceptible. Over a lifetime, the positions of stars change only slightly. From a physical perspective, these motions are steady and precise. Gravity continues to act at this scale, but its influence is spread out. No single star dominates the motion of a neighborhood. Instead, each star responds to the combined gravitational field of many others, along with the larger structure of the galaxy. This shared field smooths motion. Extreme deviations are rare. Abrupt changes require strong interactions, and those interactions are uncommon in such sparse environments. The average distance between stars in a neighborhood is several light years. At these distances, direct gravitational encounters are infrequent. Stars pass by one another quietly, without disruption. Planetary systems within these stars remain largely unaffected by neighboring stars. The space between stars provides stability. This separation is one of the reasons planetary systems can persist for billions of years. Stellar neighborhoods exist within larger galactic structures. As stars move, they trace paths determined by the gravitational shape of the galaxy itself. These paths are long arcs around the galactic center. A single orbit around the center of a galaxy can take hundreds of millions of years. During that time, a star may pass through different regions of the galaxy, encountering different stellar densities. Even so, its motion remains smooth. The galaxy does not pull sharply, it guides gently. The gravitational field of a galaxy is distributed across vast amounts of mass, including stars, gas, and dark matter. This distribution creates a broad, shallow potential. Within this potential, stars move predictably. Their orbits are not perfectly circular, but they are stable. Small variations average out over time. This averaging is a recurring theme at larger scales. As systems grow in size, individual irregularities matter less. The behavior of the whole becomes smoother than the behavior of the parts. This is why stellar neighborhoods appear calm. Each star follows simple rules, but the collective result is orderly. The same physics that governs particles and planets governs stars and neighborhoods. Mass attracts, motion persists, interactions accumulate slowly. Nothing at this scale requires constant adjustment. Once stars settle into their galactic paths, they tend to remain there. Occasionally, interactions occur. A star may pass close enough to another to slightly alter its trajectory. A cluster may encounter a denser region of the galaxy. These events unfold over long timescales. Their effects propagate gradually. There is no sudden reorganization. The system absorbs change, From the perspective of physics, this absorption is key. It prevents runaway instability. It ensures continuity. Stellar neighborhoods are not static, but they are durable. They evolve quietly. Stars age, change, and eventually end their lives. New stars form elsewhere, yet the overall structure persists. Motion continues. Paths repeat. Patterns endure. When viewed from far enough away, the galaxy appears as a steady, rotating system. The motion of individual stars blends into a smooth flow. This flow is the combined result of countless small motions, each governed by the same simple principles. Inertia carries stars forward. Gravity curves their paths. Time smooths irregularities. The universe does not need to enforce order at this scale. Order emerges naturally. From planetary systems to stellar neighborhoods, the transition is seamless. There is no boundary where physics changes its behavior. The same rules apply. Only the distances grow larger. Only the timescales become longer. And with those longer timescales comes an even greater sense of calm. Because when change unfolds slowly enough, it feels almost permanent. And that is the character of the universe at the scale of stars. As stellar neighborhoods expand outward, they merge seamlessly into the larger structure of a galaxy. A galaxy is not a collection of stars moving independently. It is a coordinated system shaped by gravity, acting across enormous distances. Each star carries its own motion, but that motion is guided by the combined gravitational influence of the entire galaxy. This influence is not concentrated in one place. It is spread out. The mass of a galaxy includes stars, clouds of gas, dust, and a large amount of unseen matter. Together, this mass forms a gravitational landscape that changes slowly and smoothly. Within this landscape, stars follow long, curved paths. These paths are often described as orbits, but they differ from planetary orbits. They are broader, less rigid, and shaped by the collective mass of billions of objects. A single star does not orbit a point. It moves through a region where gravity varies gradually. Because the gravitational field is extended, motion becomes smooth. Sudden changes are rare. Sharp turns do not occur. Instead, stars drift along paths that repeat over hundreds of millions of years. From within a galaxy, this motion feels almost imperceptible. Over short timescales, stars appear fixed relative to one another. Over long timescales, patterns emerge. Galactic disks form when large numbers of stars share similar angular momentum. This shared rotation flattens the system. Stars move in the same general direction, tracing wide arcs around the galactic center. The disk does not behave like a solid object. Different regions rotate at different speeds. Inner regions complete orbits more quickly. Outer regions move more slowly. but not as slowly as expected from visible matter alone. This observation led to the idea that additional mass must be present. That mass does not emit light. It does not interact strongly with ordinary matter. Its presence is inferred from motion. This unseen mass contributes to the smoothness of galactic rotation. By spreading gravitational influence over large volumes, it stabilizes the system. Without it, galactic disks would not persist in their observed form. The result is a structure that resists disruption. Spiral arms emerge within this rotating disk. They are not fixed collections of stars. They are regions of slightly higher density that move through the disk like waves. As stars pass through these regions, their motion changes only slightly. They continue along their paths afterward. The arms appear stable because the pattern persists, even though the individual stars move on. This behavior reflects a broader principle. At large scales, structure often exists as a pattern rather than a collection of fixed parts. The pattern endures. The components flow through it. This reduces stress within the system. It allows change without collapse. Above and below the galactic disk, stars occupy a halo. These stars follow more varied paths, often elongated and tilted relative to the disk. Their motion is still governed by gravity, but with fewer constraints. Even so, their paths are stable. They complete long journeys around the galactic center without interruption. The galactic center itself is dense, but it does not dominate motion sharply. Its influence is blended with that of the surrounding mass. Stars near the center move more quickly, but their motion remains smooth. Nothing pulls them inward suddenly. The galaxy as a whole behaves like a gently rotating system. It does not require constant input of energy. It does not need correction. Its structure arises from initial conditions and persists through balance. Galaxies interact with one another, but these interactions are slow. When galaxies pass near each other, tidal forces stretch their outer regions. Stars respond gradually. Arms may lengthen, shapes may change, but even these interactions unfold over hundreds of millions of years. There is time for motion to adjust. There is time for energy to redistribute. Collisions between stars remain rare. The vast distances between them provide safety. This spacing allows galaxies to evolve without internal chaos. Over time, galaxies settle into forms that reflect their history. Some become thin disks. Others become rounded or irregular. Yet all are governed by the same physics. Mass attracts. Motion persists. Change unfolds slowly. The scale of a galaxy amplifies calm. At this size, individual disturbances fade into the background. The collective behavior dominates. From the perspective of deep space physics, galaxies represent a balance between motion and structure. They are large enough to smooth irregularities. They are cohesive enough to maintain identity. They exist as long-lasting patterns within the universe. Stars are born, age, and disappear within them. The galaxy remains. This persistence is not static. It is dynamic stability. Motion continues everywhere. Paths curve gently. Patterns repeat. At this scale, physics favors continuity. The same rules that shaped planetary systems and stellar neighborhoods now shape entire galaxies. Only the distances are larger. Only the timescales are longer. And with those longer timescales comes an even deeper sense of order. Because when motion unfolds slowly enough, it blends into stillness. And that stillness is not the absence of activity. It is the presence of balance. Within a galaxy, motion does not end at structure. It continues as flow. A galaxy is not only a shape, it is a system in motion. Every star, cloud of gas, and region of dust participates in a shared movement, guided by gravity and inertia. This movement is not chaotic. It follows broad, predictable patterns. The primary motion of a galaxy is rotation. Stars orbit the galactic center along wide, curved paths. These paths are shaped by the combined mass of everything in the galaxy. The center does not pull sharply. It guides gently. Because the gravitational influence is distributed across a vast volume, motion remains smooth. No single region dominates completely. As stars move, their paths are influenced by the surrounding mass rather than by any one object. This creates a form of collective balance. In this balance, motion persists without accelerating out of control. Galactic rotation is slow when measured against human time. A single orbit around the center of a galaxy can take hundreds of millions of years. During that time, the position of a star changes gradually. From one year to the next, the difference is negligible. This slow pace is one of the defining features of galactic motion. It allows systems to absorb disturbances. Small changes average out. Irregularities smooth themselves over time. Within a rotating galaxy, stars at different distances from the center move at different speeds. Inner regions complete their paths more quickly. Outer regions move more slowly, but remain connected to the overall motion. This variation does not tear the galaxy apart. Instead, it produces a stable gradient of motion. Each region moves in a way that reflects the gravitational environment it occupies. Gas within the galaxy responds in a similar way. Diffuse clouds drift along with the rotation, slowly compressing and expanding as they pass through denser regions. This gentle cycling supports long-term structure. It allows material to move without sudden collapse. Spiral patterns emerge naturally within this flow. They are not rigid arms made of fixed stars. They are regions where motion briefly aligns, increasing density. As stars and gas pass through these regions, they slow slightly, then resume their paths. The pattern persists even as the components change. This pattern-based structure reduces stress within the system. It allows order to exist without rigidity. Galactic balance is also influenced by mass beyond the visible stars. The gravitational field extends far beyond the luminous disk. This extended influence shapes motion at the edges of the galaxy. It prevents outer regions from drifting away. It maintains coherence across enormous distances. Because of this extended gravitational landscape, motion remains bound. Stars do not escape easily. Their inertia is balanced by gentle curvature. This balance defines the outer limits of the galaxy. Over long periods, galaxies evolve. Their shapes change slowly. Interactions with other galaxies can stretch or compress their structures. Yet even during these interactions, motion remains gradual. Stars respond over time. Energy redistributes. New equilibrium emerges. This process does not rush. The scale of galaxies ensures that nothing happens quickly. Even dramatic events unfold across spans of time that allow adjustment. This slowness is essential to stability. It allows motion to remain smooth. It allows patterns to persist. From a physical perspective, galactic motion represents a system operating near equilibrium. Energy is neither concentrated nor dissipated rapidly. It circulates. Momentum is conserved. Forces are balanced across large regions. The result is a dynamic but calm system. Galaxies do not require constant input to maintain their structure. They persist because the underlying physics favors continuity. As long as mass remains distributed and motion remains bounded, the system endures. At this scale, the universe reveals one of its most consistent behaviors. Large systems tend toward smooth, collective motion. Individual variations become less important. The whole dominates the parts. This dominance does not erase individuality. Each star follows its own path. Each region evolves at its own pace, but together they form a coherent flow. This flow is not directed toward an endpoint. It continues. It repeats. It adapts slowly. From planetary systems to stellar neighborhoods to entire galaxies, the progression is seamless. The same principles apply. Only the scope changes, and as the scope increases, the pace slows. Motion stretches across time. Change becomes gentle. Balance becomes the defining feature. At the scale of galaxies, physics favors endurance. Systems persist not by resisting change, but by absorbing it gradually. This absorption is what allows the universe to remain ordered over billions of years. And it is this quiet, persistent motion that defines the calm character of deep space. Beyond individual galaxies, motion continues to scale upward. Galaxies are not isolated objects suspended in emptiness. They exist within larger environments shaped by gravity, acting across vast distances. These environments are known as galaxy groups and clusters. A galaxy group contains a few to dozens of galaxies moving together. A galaxy cluster may contain hundreds or thousands. Within these collections, gravity operates in a familiar way. Each galaxy carries momentum inherited from its formation and early interactions. That momentum persists. As galaxies move through space, they respond to the combined gravitational influence of their neighbors. No single galaxy dominates the system completely. Instead, motion reflects the average distribution of mass. This averaging produces smooth behavior. Galaxies follow long, curved paths within clusters. Their motion is slow. A single pass across a cluster can take billions of years. Because of this, interactions unfold gradually. When galaxies approach one another, their outer regions feel tidal forces first. Stars at the edges respond gently. Paths stretch slightly. Shapes distort slowly. The core regions remain largely unaffected for long periods. This separation of scales is important. It prevents sudden collapse. It allows systems to adapt without breaking. Galaxy clusters themselves are not static. They evolve over time. Smaller groups merge into larger clusters. Isolated galaxies drift inward. Yet even these mergers occur slowly. The distances involved are immense. The gravitational pull increases gradually as mass accumulates. Motion adjusts over long spans of time. At even larger scales, clusters connect to one another. They form extended structures known as filaments. These filaments stretch across hundreds of millions of light years. Along them, galaxies and clusters move slowly toward regions of higher density. Between filaments lie vast voids. These voids are among the quietest regions in the universe. They contain very little matter. Motion within them is minimal. The presence of voids contributes to large-scale balance. Matter is not evenly distributed, but the contrast unfolds smoothly. From a distance, the universe resembles a web. This web is not rigid. It is dynamic. Galaxies flow along its strands, guided by gravity and inertia. Nothing in this structure requires precision. The patterns emerge naturally from the initial distribution of matter and the passage of time. At these scales, gravity acts collectively. Individual interactions matter less. The overall shape of the mass distribution becomes dominant. This dominance smooths motion further. Irregularities fade into the background. The universe becomes calmer as scale increases. This may seem counterintuitive. Larger systems contain more mass and more energy, yet their behavior is gentler. This gentleness arises from distance. When objects are separated by vast spans of space, interactions weaken, forces spread out, acceleration decreases, change slows. The expansion of the universe also plays a role. Space itself stretches over time. This stretching does not disrupt bound systems like galaxies or clusters, but it influences the motion between them. At the largest scales, expansion counterbalances gravitational attraction. Galaxies drift apart slowly unless gravity binds them together. This balance between attraction and expansion defines the structure of the cosmos. Neither effect dominates completely. The result is a universe that evolves without rushing. Large-scale motion becomes subtle. Patterns change slowly. From moment to moment, almost nothing appears to happen. Yet over billions of years, structure emerges, shifts, and settles. From a physics perspective, this behavior reflects a system operating near equilibrium. Energy is distributed across immense volumes. Gradients are shallow. There are no sharp boundaries. The universe does not seek a final arrangement quickly. It explores possibilities gradually. At this scale, the familiar rules still apply. Mass attracts. Motion continues. Paths curve gently. The difference lies in the timescale. Processes that take minutes on Earth take millions of years in space. Processes that take years take billions. This stretching of time transforms motion into something that feels permanent. Galaxies appear fixed. Clusters seem unmoving. The cosmic web looks frozen. But beneath this appearance, motion continues steadily. Everything remains connected through gravity. Nothing acts alone. The universe behaves as a single, vast system, composed of smaller systems nested within one another. From planets to stars, from stars to galaxies, from galaxies to the cosmic web, the transition is continuous. There is no abrupt change in behavior, only a steady widening of scale. As scale increases, variation decreases. As variation decreases, stability grows. This is why the largest structures in the universe are also the calmest. They embody motion spread so thinly across time and space that it becomes almost indistinguishable from stillness, and it is within this near stillness that the universe carries most of its mass, its history, and its enduring order. At the largest scales, structure and time become inseparable. The cosmic web does not simply exist in space. It unfolds across deep time. Every filament, cluster, and void reflects processes that began billions of years ago and continue quietly into the present. When matter first began to gather in the early universe, it did so unevenly. Tiny variations in density, almost imperceptible, shaped everything that followed. These variations did not grow quickly. They grew steadily. Gravity amplified them slowly, allowing matter to drift, gather, and settle. The result was not sudden structure, but gradual organization. As the universe expanded, distances increased. Expansion stretched space itself. This stretching slowed the growth of new structures while preserving those already formed. Bound systems remained intact. Unbound regions drifted apart. This balance between gravity and expansion defines cosmic continuity. It prevents collapse from dominating. It prevents dispersion from erasing structure entirely. Time plays a central role in this balance. At cosmic scales, time is not experienced as a sequence of moments. It is experienced as duration. Processes unfold across spans so long that change becomes subtle. A galaxy evolves over billions of years. A cluster forms over even longer periods. The cosmic web itself reflects the accumulated motion of matter since the universe was young. From one year to the next, nothing noticeable happens at this scale. From one century to the next, very little changes. This slow pace is not inactivity. It is motion extended across time. Deep time allows systems to settle. It allows energy to redistribute. It allows irregularities to smooth out. When viewed across deep time, the universe favors continuity over disruption. Violent events occur, but they are localized. A supernova may briefly release enormous energy, but its effects dissipate into the surrounding space. A galaxy collision may rearrange structure, but it unfolds over hundreds of millions of years. Even dramatic events are softened by duration. The vastness of time absorbs intensity. From a physical perspective, this absorption is essential. It allows the universe to remain coherent. If changes occurred rapidly everywhere, structure could not persist. Instead, most regions experience long periods of quiet evolution. Matter drifts, radiation spreads, energy differences decrease. This gradual evening out is a recurring theme. As time progresses, contrasts lessen. Dense regions become less dense. Sparse regions receive small amounts of matter. Temperature differences smooth. The universe does not rush toward uniformity, but it trends in that direction. This trend does not erase structure immediately. It operates gently. Galaxies continue to shine. Clusters remain bound. Yet beneath this persistence lies a slow movement toward balance. Deep time allows this movement to remain calm. Nothing needs to be forced. Processes unfold at the pace set by physical laws and scale. At these scales, the future does not feel urgent. It feels distant. From a cosmic viewpoint, billions of years are a manageable interval. Stars form, age, and fade. Galaxies grow, interact, and settle. Through all of this, the overall structure of the universe remains recognizable. The same patterns repeat at different times. The same principles apply. Gravity shapes motion. Inertia preserves paths. Expansion moderates interaction. These influences do not compete aggressively. They coexist. Their coexistence produces continuity. Continuity does not mean stagnation. It means that change occurs without abrupt transitions. The universe evolves by adjustment rather than replacement. This style of evolution favors stability. Systems that persist do so because they adapt slowly. They absorb disturbances. They redistribute energy. They remain recognizable across immense spans of time. Deep time gives meaning to cosmic calm. Without deep time, motion would feel chaotic. With deep time, motion becomes smooth. The longer the time scale, the gentler the change appears. At the scale of the universe, time stretches far beyond intuitive understanding. Yet physics remains consistent. The same rules that govern particles and planets govern clusters and filaments. Only the duration changes. As duration increases, variation fades. As variation fades, order emerges. This is why the universe, when observed from a sufficiently distant perspective, appears calm. It is not because nothing happens. It is because everything happens slowly. And in that slowness, continuity becomes the dominant feature. The universe continues, not by resisting change, but by unfolding it across time so vast that each moment blends into the next. From structure to structure, from era to era, the motion never stops. It simply stretches. And in that stretching, the universe maintains its quiet, enduring balance. As time extends further, the universe's behavior becomes increasingly defined by balance. This balance is not a fixed state. It is a tendency. Over long durations, systems move toward configurations that change more slowly. Energy spreads out. Motion becomes smoother. Differences lessen. This tendency is often described as a movement toward equilibrium. Equilibrium does not mean nothing happens. It means that large-scale changes become rare. At cosmic scales, equilibrium emerges because energy is distributed across enormous volumes. When energy is concentrated, change is rapid. When energy is spread thinly, change slows. As the universe expands, the same amount of energy occupies more space. This expansion reduces gradients. Steep differences flatten. Sharp contrasts soften. Gravity still acts, but its influence weakens with distance. Bound systems remain intact. Unbound regions drift apart. This separation allows the universe to maintain structure without crowding. Clusters persist. Galaxies remain cohesive. Yet the spaces between them grow quieter. Radiation plays a role in this process. Light emitted by stars and galaxies travels outward, carrying energy away from its source. As it travels, it stretches. Its wavelength increases. Its energy decreases. This gradual redshifting spreads energy across time and space. Nothing is lost abruptly. Energy thins gently. The background glow of the universe reflects this process. It is uniform, faint, and steady. This uniformity is a sign of equilibrium emerging at the largest scales. It does not erase structure, but it sets a calm backdrop. Against this backdrop, Local systems continue their quiet evolution. Stars orbit, galaxies rotate, clusters drift. Their motion persists because equilibrium does not require stillness. It requires balance. Balance allows motion to continue without escalation. This is why the universe does not collapse inward everywhere at once. It is also why it does not disperse instantly. The competing influences of gravity and expansion settle into a long-term coexistence. Neither dominates completely. Over time, the rate of change slows further. Processes that once reshaped structure become less frequent. Star formation declines. Large mergers become rarer. The universe does not stop evolving. It simply evolves more slowly. This slowing is not imposed. It arises naturally from scale. As systems grow larger and more diffuse, interactions weaken. Weaker interactions lead to gentler outcomes. At this stage of cosmic evolution, continuity becomes the defining feature. Change unfolds, but it does so quietly. From one era to the next, patterns remain recognizable. The universe remembers its past through structure. Galaxies carry the imprint of earlier conditions. Clusters reflect ancient motions. Deep time preserves these patterns by allowing them to persist. Equilibrium, in this sense, is not an endpoint. It is a direction. The universe does not reach perfect uniformity suddenly. It approaches it gradually, asymptotically. Each step forward is smaller than the last. This gradual approach ensures calm. Nothing needs to be resolved quickly. From a physics standpoint, this behavior is expected. Systems with many degrees of freedom tend toward states where energy is evenly shared. At cosmic scales, the number of degrees of freedom is immense. The result is slow, collective motion. Local disturbances become insignificant compared to the whole. This does not eliminate complexity. It embeds complexity within a stable framework. The framework endures even as details change. Equilibrium provides context. It allows the universe to continue without urgency. Motion continues, but it no longer drives dramatic reorganization. The pace becomes steady, predictable, smooth. At this scale, the universe exhibits one of its most consistent traits. It prefers gradual transitions over abrupt ones. It spreads energy rather than concentrating it. It favors balance over extremes. From deep time to cosmic equilibrium, the shift is subtle. There is no moment when equilibrium suddenly arrives. There is only a continuous movement toward calmer conditions. This movement defines the long-term character of the cosmos. It ensures that the universe remains comprehensible across eras. It ensures that structure persists without constant upheaval. And it ensures that motion, though unending, remains gentle. In this way, equilibrium is not the absence of activity. It is the presence of sustained balance, a balance that allows the universe to continue unfolding, quietly, across time that stretches beyond ordinary measure. As equilibrium becomes more influential, the universe's future is shaped less by dramatic events and more by gradual trends. The same physical principles that govern the past continue forward. Nothing fundamentally changes about how matter and energy behave. Only the conditions evolve. Over long periods, regions of high activity become rarer. Stars continue to age. They convert fuel into light and heat at steady rates. Eventually, that fuel diminishes. This process does not accelerate, it slows. New stars still form, but less frequently. The gas needed for star formation becomes more diffuse. It spreads across larger volumes of space. Gravity continues to gather matter, but with less material available, the pace decreases. Galaxies retain their structure, but their internal activity gradually quiets. Bright, short-lived stars disappear first. Long-lived stars remain. This shift changes the character of galaxies. They become calmer. Their light becomes steadier and less intense. Clusters of galaxies persist as bound systems. Their motion continues, but interactions become infrequent. Galaxies orbit within clusters over billions of years, rarely colliding. When collisions do occur, they unfold slowly. Energy redistributes. New equilibrium emerges. At even larger scales, the expansion of the universe continues. Space itself stretches. Distances between unbound galaxies increase. This expansion does not pull matter apart violently. It simply allows space to grow. Bound systems remain unaffected. Clusters hold together. Galaxies remain intact. Planetary systems persist. The influence of expansion becomes significant only across vast distances. Over time, regions beyond clusters drift farther apart. Communication between them becomes limited. Light takes longer to travel. Eventually, some regions fade from view. This fading is not sudden. It unfolds gradually. The universe does not switch states. It transitions. Radiation continues to spread. As it travels, its energy decreases. The background glow becomes fainter, yet it remains uniform. Uniformity is a hallmark of equilibrium. At this stage, the universe's behavior is dominated by persistence rather than transformation. Most structures that exist will continue to exist for long periods. Change occurs, but at diminishing rates. From a physical perspective, this trend reflects the universe's movement toward states of lower available energy. Not lower total energy, but lower usable energy. Energy becomes evenly distributed. Differences flatten. When differences are small, processes slow. This slowing is not decay. It is stabilization. The universe does not lose its ability to function. It simply functions in a quieter way. Motion remains. Particles continue to move. Orbits persist. but large-scale reorganization becomes rare. Deep time extends far beyond the formation of stars and galaxies. It includes eras where existing structures persist with minimal change. White dwarf stars cool slowly. Neutron stars spin steadily. Black holes continue to influence their surroundings through gravity alone. These objects endure. They represent matter in stable configurations. Their existence reflects the universe's preference for states that change slowly. Over immense spans of time, even these remnants evolve. Cooling continues. Rotation slows, yet nothing happens abruptly. Physics maintains continuity. The long future of the universe is not empty. It is sparse. Activity does not vanish. It thins. The pace of events stretches. Moments become eras. Eras become indistinguishable. At this scale, time loses sharp boundaries. The universe approaches a condition where change is minimal, not absent, but subtle. Equilibrium becomes the dominant theme. This does not mean that all structure disappears immediately. It means that structure persists without frequent renewal. The universe carries forward what it has already formed. From a physics standpoint, this is a natural outcome. Systems evolve toward configurations that require less adjustment. Once those configurations are reached, they remain. The universe does not need to seek an endpoint. It continues according to its rules. These rules favor smooth transitions. They favor balance. They favor endurance. From the present moment into the far future, the same gentle processes continue. Stars age, galaxies drift, clusters remain bound. Expansion proceeds quietly. Nothing interrupts the flow. The universe remains coherent. It does not fracture. It does not collapse entirely. It unfolds, and as it unfolds, the pace continues to slow. This slowing is not a sign of exhaustion. It is a sign of stability. The universe has spent billions of years establishing patterns that endure. Those patterns carry forward. They define the long future. From cosmic equilibrium to the quiet persistence of structure, the trajectory is clear. The universe continues, not by accelerating toward an end, but by extending its calm behavior across time that has no practical limit. And in that extension, motion remains gentle, change remains gradual, balance remains. Thanks for spending this time with us. If this exploration of deep space physics was helpful, you can support the channel by liking the video and subscribing to Cosmic Sleep Lab. And if there's a topic you'd like to drift through next, a part of the universe you'd like to learn or nap with, feel free to share it in the comments. Until next time.